So yesterday we met one of our two new friends, which is going to become now a parent function for which we're responsible for sketching quickly transformations of, and that friend was who? Sahala. Yeah, Sahala. And of course it's a mnemonic device. S stands for shrimp. Sine. Good. And then the ahala is axis, high axis, low axis. So you have 5 critical values, which are your quadrantal angles, and those tell you where to put your values in relation to the sinusoidal axis, and then the high and low points so that you can sketch one cycle. What is the length of one cycle? 2 pi, and we call that the period, right, which is the same thing in science as the, not quite, frequency, the wavelength, yeah. So how are the wavelength and the frequency related? They are reciprocals of each other. Yeah, the period measures how long it takes to make one cycle, and the frequency tells you how many cycles you have in a fixed distance, okay? But they kind of measure the same thing. It's a rate. All right, so if we're going to sketch Sahala, and we did this again yesterday, but I'm going to do it today again, this is going to be kind of what you're going to be doing quite a bit of. You come out an arbitrary distance, not quite the end, and you call it 2 pi. You bisect it on your paper, and you bisect it again. So when you bisect that distance twice, the idea is that you have your quarter cycle counting interval prescribed. Quarter cycle means you have your critical values marked, right? And then you bisect this one, and of course you label that as 3 pi halves, and you still have 0 over here. The amplitude is what for sine? What is the amplitude? It's the wave height. It's how high it oscillates above and below the center line, which is the x-axis, also the sinusoidal axis. It's 1. So this graph is going to be contained between -1 and 1. So now that you set the table, you put the food out on the table. Putting the food out on the table is putting your dots, and that's where the Sahala comes in. So it's axis, high, axis, low, axis. And if you needed more dots, you could just continue the pattern then every quarter cycle, counting by pi halves. And now you eat. Eat means you connect the dots, as far as the analogy goes. And you want to connect your dots with smooth quarter cycle arcs, okay? From 0 to pi halves, this function is increasing, and we say it's concave down like a frown. From pi halves to pi, it's decreasing concave down like a frown. And then the curvature, or the concavity, as we say, changes at pi, because now it goes from part of a frown to part of a smile. So from pi to 3 pi halves, it's decreasing concave up, and from 3 pi halves to 2 pi, it's increasing concave up like a cup, right? So you do want to exaggerate the point at pi. This point right here at pi, in general, is where the curvature changes. Now, curvature we call concavity. Concavity is another word for curvature. In physics, you have concave and convex. In math, we don't have convex. We just have concave up and concave down. So the concavity is the curvature. They're interchangeable. And at this point, the concavity changes. It changes from concave down like a frown to concave up like a cup or a smile. And the point where the curvature changes, we call a what point? Inflection point. Yeah, we've had that before. So there is your inflection point. That is a graphical manifestation. And so you want to exaggerate that point on the x-axis. Right? We called that an M3 root back in the day on the cubic function. Okay, so we have an inflection point there. We also have right here at pi halves, we have a local maximum. And down here at -1 at x equals 3 pi halves, we have a local minimum. Now remember, the local max and local min are x or y values? Y values, yeah. So we'll say we have a local maximum of 1 at x equals pi halves, and we have a local minimum of -1 at x equals 3 pi halves. Okay, so what we want to do is keep talking about this function. If we want to create the stamp, let me go ahead and do that just with the graph. I'm going to copy that, and I'm going to paste it over here to the left and do that. And what's nice is now I can just put negatives. I can change that to negative pi halves, negative pi, negative 3 pi halves. And then this would be over here, not 0, but negative 2 pi.
When doing that, is that required again to do that? And listing all the characteristics?
Yeah, because I want to see what it looks like a little bit to the left of the y-axis as well. This is one cycle, and I'm always going to have you sketch at least 2 cycles, always, at least 2 cycles. And thank you. Yes, he's here. So if you sketch one more cycle to the left, that helps with symmetry. Because when you're looking for symmetry, you want to look for what? What 2 types of symmetry do we have? Y-axis symmetry for sure. That's folding symmetry. That would mean the function is what? Even, odd, or neither. If a function has y-axis symmetry, it's even, right? We talked about that. And if a function has origin symmetry, that's the rotational symmetry, then it's an odd function. So having another cycle on the other side helps us see that. Does this function have either of those 2 symmetries? Is it even, odd, or neither? Well, even would be y-axis symmetry. If you fold this graph on the y-axis, does it coincide with itself perfectly on the other side? No. But remember, origin symmetry is rotational symmetry. If you take your graph and you rotate it upside down with your finger on the origin, does it appear to be the same graph? Yes, okay? This one has rotational symmetry. So it's origin symmetry, we call it, which means it's an odd function. Now remember the algebraic consequence of an odd function, or the test. We said back in the day, if f of negative x equals the opposite of f of positive x. That's the test for the odd function, right? You plug in a negative x, if all the signs change, it's odd. What that means for sine is this. That means sine of negative theta, or we're using x now, I should say. Sine of negative x is equal to negative sine of positive x. And on the first go around on the test, that was one of the questions on the multiple choice, right? I gave you what sine of theta was, and then I asked you what sine of negative theta was. And back then, you had to draw where the angles could have lived and then rotate in the opposite direction. And it turns out that the sine value changes. On the next test, some of y'all just assumed that was true for cosine because you didn't think about it or draw out your angles, and so you got the wrong answer. But sine is an odd function, okay? So sine of negative x is the same as negative sine of positive x. Let's look at the domain. What is the domain of sine? It's the set of all angles x such that x is what? We have 2 cycles drawn there. How many more cycles could we draw? Infinitely many. Remember I talked about the stamp, 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 stamp. I'd be there forever and ever and ever. Are there any x values that don't have y values for the graph of sine? Or is that graph continuous everywhere? Yeah, so the domain is all real numbers. So it's the set of all x such that x is an element of the real numbers, or you could just say double bar r, or you could say negative infinity to infinity. Now that should make sense to you as well in terms of the definition, because remember sine of theta is y over r, and the only time sine is undefined in its ratio is when the denominator is 0. When is the radius of a circle 0? Never, when you don't have a circle. It's called a single point. So r is never 0. X and y can be 0, but r in the denominator can never be 0. So sine is never undefined. Ergo, its domain is all real numbers. What is the range of sine? 1? Can't go past 1. And negative 1. So how do we list that? Yeah, the set of all y's, and then negative 1 less than or equal to y less than or equal to 1. That would be set builder notation. You could also do it in interval notation, beefy bracket, negative 1, comma 1, beefy bracket. Right? Yes?
Could you also put 1 greater than y greater than negative 1?
No. No. The compound inequality is always reserved for the and case and it always has to be less than. So when you do it like this, you have your alligators eating the correct number, but that's bad grammar. That's like using a contraction in English, okay? When you're using the compound inequality, it should always be from least to greatest. And when you list it like that, you have your bigger number on the left and your smaller number on the right. So it's just poor notation. Okay? So always try to go from least to greatest. So there's the range. So we can't have any sign values bigger than 1 or smaller than -1. Does that make sense in terms of the ratio here? The sign ratio is the ratio, again, we've talked about it, of one of the smaller sides, y, to r, which is the funny word, hypotenuse, which is always the longest side. So if you have a sign ratio bigger than 1, now you're saying that one of your shorter sides is bigger than the longest side. And that'll make your brain freeze worse than eating a slushie in one gulp. That's not true. All right, so what else? Domain, range, we talked about symmetry, and behavior. How do we show that we're analyzing end behavior? What mathematical notation do we use? Limit. Good. Which limit? The limit as x approaches, where's the end of the graph? That way. Good. Infinity of f of x. What is it? There's only a couple of things that can happen, we said, right? Either the graph increases without bound, like x squared, in which case the limit is infinity. It doesn't exist because it increases without bound. It either decreases without bound, so negative infinity. It tapers off towards the horizontal asymptote. Or what does this do? It oscillates constantly as you go out to the right between what? -1 and 1. So is there a limit to what the y values are doing? There is? Well, you could say it's bounded. It's going to be bounded between -1 and 1. But is there a single y value that is the limiting value? No. So in this case, the limit d and e. You have to put d and e. You can't put infinity because the y values don't go up forever. You can't put negative infinity. You can't put 1. You can't put -1. You can't put 1/2. If you go out at any point, put your finger down on the graph, it could be anything between -1 and 1. There is no single value. So you could say d and e, if you want, by oscillation. Okay, d and e by oscillation. Intercepts. What kind of intercepts are we talking about, x or y? X or y intercepts. Which are your favorite? Both. Good, both. That's what we mean, intercepts, both. Well, what's the y-intercept? That's the easiest one. 0, yeah. And then it has several x-intercepts. What are the x-intercepts? Every multiple of pi, yeah. So let's list that. We have x-intercepts, which are also your axis points at x equals. Now, when they happen at regular intervals, here's all you have to do. You pick your favorite x-intercept. What's your favorite x-intercept up there? 0, pi, 2 pi, negative pi? You like pi? Okay. So you could say pi, and then you put multiples of how often they occur. How often do they occur? How far is it from 0 to pi or from pi to 2 pi? Pi. So you would say pi plus pi n, where n is what type of number? It can't be a real number. It can't be like 1.5. It has to be like a 1 pi or a 2 pi or a 3 pi or even a -1 pi. What types of numbers are those? Not all real. -2, -1, 0, 1, 2, 3. Positive or negative, which we call those, that's an n. It's a cursive n. You could use m if you want. It would be fine. Now, pi plus pi n works, but I have a better favorite value. I like 0. Okay? Because 0 is also an x-intercept. Not that pi plus pi n is wrong, but 0 plus pi n just simplifies to pi n. So your axis points are every multiple of pi. Let's see, what else? Max and mins, we've already talked about, and curvature changes, we already talked about. Okay? So let's just do, yeah.
What was that last figure you drew?
Figure. The z?
Yeah.
Oh, that's the number set for the integers, remember? Yeah. No, that's your z, the integers. Kind of like your real numbers, and then we have the whole numbers. Yeah. So z is an integer. That was from the beginning of the year. It's -1, -2, -3, 0, 1, 2, 3. And then the last thing, let's just list an interval where the function is increasing. Sine of x is increasing. When we list values of increasing and decreasing, are we listing x values or y values? X values. Good. We're looking for the values of x where the graph is going uphill. Let's go ahead and list the largest interval we possibly can. What if I start at -π/2? Would that work? Okay, so at -π/2, I put an open interval, because at -π/2, it's really neither increasing nor decreasing. It's a stationary point. And now that function is increasing all the way up to where? π/2. And then union, if you wanted to pick up on the next interval, where would be the next place where it's increasing? 3π/2, yeah, 3π/2. And it's not shown, but then it would increase all the way to where? Come on, infer what the graph would do past 2π. It would continue up, right, to the next high point, which would be at 5π/2. Yeah, 5π/2. And we can continue this forever and ever and ever, right? There are infinitely many intervals where the function's going uphill. And they happen every multiple of pi. Same thing with downhill. The graph is decreasing then from π/2 to 3π/2. And then from 5π/2 to 7π/2, so on and so forth. So I might ask you on a test to give me an interval of increasing, decreasing. Or I can ask a question on the test, which of the following is true regarding the characteristics of this graph? And I can ask you about the symmetry, bless you, the max mins. I can ask you about any of this stuff. And maybe 4 of the 5 answer choices are true and one of them is false. So maybe I say which one's not true. Possibly, certainly. Yeah. Anything that's related to the graph, I could ask. Anything regarding its behavior. Okay, anything else you want to say about the graph of sine before we move on to the next guy? Anything else worth noting? Is it always drawn in pink? No, you probably didn't draw yours in pink. Anything else you want to say? Origin symmetry is really good. Let's look at the consequence of that real quickly. Sine of -x equals negative sine of positive x. So if I have a negative angle, let's say negative right here. Here's my negative angle. The sine of the negative x is going to be the opposite of the sine of the positive x. They're going to be the same distance away from the x-axis, but they're going to be opposite in sign, okay? And that's true for any origin symmetric function, not just sine. Opposite x values give you opposite y values. Okay, sweet. We're not going to do the same thing for the cosine. We're going to skip example 3. But cosine is the other sinusoid. There's 2 sinusoids. Sine of x, and now you know the answer is what? Cosine of x. And it makes sense because cosine also has the name sine in it. And we already talked about what the co and cosine stood for. I gave you that hint a while back. Do y'all remember what it meant? Coterminal means sharing the terminal ray, but cosine doesn't mean sharing the sign. Co in this case means what? Complementary. Thank you. Complementary. Yeah. Did you say that? Did not hear it. Okay. Speak up. Use your outside voice. Yeah. I heard Julia over you. So sorry. I'll blame Tyler. Does that make you feel better? Okay. Yeah, complementary. And of course, complementary angles are 2 angles that add up to what? 90 degrees, or how many radians? Pi halves. Good. So the cosine function is going to be off from the sine function by 90 degrees or pi halves radians. Okay? Now, if you think about it, sine of 0 is 0, right? What is cosine of 0? Cosine of 0. Cosine of 0 is 1. What's the ordered pair at 0 on the unit circle? 1 comma 0. Cosine is the x value. Oh my gosh. Okay, so good. That's okay. It's Tuesday. It's Fat Tuesday. So cosine starts at 1. So it's sometimes said to have had a head start on the graph of sine. Sine starts at 0 and then goes up to 1. Cosine already starts at 1 at a high point. Okay? And there's only one place to go from a high point if you're sine or cosine, and that's what? Down. Okay? So the graph of cosine would look like this. If you want to get your values, we can kind of infer based upon the co-nature of it. Go ahead and get your quadrantal angles laid out. Because cosine, just like sine, is going to repeat itself every 2 pi. The maximum and minimum values of cosine have to be the same for sine, right? Because remember, cosine of theta is x over r. And it's the only other trig function in the whole wide world, first of all, that has r in the denominator, so it's going to be defined everywhere, just like sine was. But it's also the only other trig ratio other than sine that relates one of the short sides to the longest side. So it also has to be between -1 and 1. And because cosine of 0 is 1, it gets a head start on sine. You can go ahead and put your dots down. It has to be high. And it's going to oscillate the same way sine did. So the next point would be what at pi halves? Axis. And at pi it would be low. At 3 pi halves it's axis. And at 2 pi you finish at high. Now, are those the right values? What's cosine of pi halves from the unit circle? 0. And that's what we have here. What's cosine of pi? -1. Yeah, good. So if you connect those dots, you get the graph of cosine, which looks like this. It looks almost identical to sine. Turn the corner and keep it going. That's why it's the other sinusoid. It's the other sine wave. It's the cosine wave. It looks exactly like the graph of sine. It just is shifted pi halves units. Okay? If you come back one critical value over here to negative pi halves, that's where sine would be. Sine starts on the axis going up. Okay, so if you drew your y-axis right here at negative pi halves, you'd have the graph of sine. The graph of cosine is shifted pi halves units, so it has a head start. And because they only differ by a shift of pi halves being 90 degrees, we call them what kind of functions? Complementary. There you go. So that's why it's sine and the complement of sine, cosine. So how can we remember how to sketch the graph of cosine? Well, here's how we remember. C for cosine, not for cookie, although C is for cookie, and that might be good enough for you. Cosine starts where? High. Axis, low, axis, and it finishes high for one cycle. So there are your 5 critical values for one cycle of cosine. So this is the fraternal twin to Sahala. It's her sister, Chala. The final H is silent. Don't try and say Chala. It's silent. It's the silent H at the end. Chala. Not Chala. All right? So you got 2 twins, Sahala and Chala, which sound funny, but if you've read Freakonomics, you know that it really happened. There were 2 people, brothers, twins, that were named Orange Jello and Lemon Jello. But they weren't pronounced Orange Jello and Lemon Jello. They were pronounced Orangelo and Lamangelo. And that really happened. It was spelled Orange Jello, no space, and Lemon Jello, no space. But it was pronounced Orangelo and Lamangelo. So Sahala and Chala seem pretty normal names compared to that, right? Yeah. All right, so Sahala and Chala. So here's your mnemonic device for one cycle of cosine. C for cosine, high, axis, low, axis, high. There's your 5 critical values for one cycle. All right, let's talk about some of the characteristics of cosine. If you want to go ahead and extend it out a little bit to the left, just so we can talk about the symmetry. Let's do domain first. It's one of the first things we should consider. What's the domain of cosine? What's that? Louder? All real numbers. Okay. Was that Caden or Zane? It was Zane. Okay. All real numbers. Good. What's the range? Sorry, should I write same S sign? How about negative 1 to 1? We'll just go ahead and list it. It's actually easier, right? Negative 1 to 1. You can use interval notation. It's good. All right. Any symmetry? That's a good one. Even, odd, or neither. Y-axis symmetry, rotational origin symmetry, or neither? This one has y-axis symmetry. Yeah. If you were to fold this graph on the y-axis, it would coincide perfectly with each other. So any function that has y-axis symmetry, we say is what? Even. It has y-axis symmetry, which means it's an even function. And remember, the consequence for an even function was that f of negative x was not equal to the opposite of f of x, but rather equal to f of x. Because now you're saying it don't matter if you plug in a negative input or a positive input, you're going to get the same output because of the symmetrical nature on either side. Okay? So if you look right here, plug in this negative value, you're going to get this. Plug in the positive version of it, you're going to get the same y value. And it doesn't matter where you go. They're y-axis symmetric. So what does that mean specifically then in terms of cosine? Well, it means that cosine of a negative angle is equal to cosine of the positive angle. And on the second version of the exam, the very first question on the test required you to discover that. Okay? Because a lot of you try to change the sign of the ratio for negative theta, but it's the same as cosine of positive theta. Okay, so it doesn't work that way. And how were you expected to figure that on the test? Well, you would say, okay, if I have a negative theta, because I asked you what cosine of negative theta is. So if theta lives over here, because I gave you a negative ratio, right? So cosine is negative in quadrants 2 and 3. And so theta could have lived over there, or theta could have lived over here. Well, if theta is, in fact, the first one, then negative theta would be over here, which also puts you in another quadrant where cosine is negative. And if it was the other one, it would put you over here. That would be your negative theta. And that also puts you in a quadrant where cosine is negative. So that's a unit circle proof, essentially, that cosine of positive theta and cosine of negative theta are the same. They're both going to rotate you into quadrants where cosine is negative. Okay, sweet. So now we know that for a fact. How about what else? End behavior. Any end behavior here? It's D and E again. Limit as x goes to infinity or negative infinity is D and E by oscillation. It has no end behavior, except that it oscillates between two fixed values, negative 1 and 1. What else? Let's see. Max and mins, yeah. We have a local maxes. There's a local max of 1 now at 0 and 2 pi and 4 pi. And we have local mins of negative 1 at pi and 3 pi and 5 pi, so at odd pi's. We still have inflection values. They occur on the axes. Just like for sine, the axis points are different now. Cosine is 0 at odd pi halves. Odd pi halves. Pi halves, 3 pi halves, 5 pi halves, 7 pi halves. We can list intervals of increasing, decreasing. Let's go ahead and list an interval of decreasing. This function is decreasing on the open interval from 0 to what? 0 to pi. Good. Union, it would pick back up where? 2 pi, and then it's not drawn, but you can infer then it would cruise all the way to? It decreases for an interval from 0 to pi. That's a pi distance. So it also decreases from 2 pi to the next pi, which would be 3 pi. Yeah. And if you needed to draw that out, what's nice is once you have one cycle with the Sahala or Chala method, you can just continue the same pattern. High axis, low axis, high axis, low axis, high axis, low, and just keep putting critical values down the same space, and then just label them, because you're counting always by your quarter cycle interval, which is pi halves. 1 pi halves, 2 pi halves, 3 pi halves, 4 pi halves, 5 pi halves, 6 pi halves, so on and so forth. Okay, so there you go. So now we have our two new parent functions, Sahala and Chala. They both pass the vertical line test. Oh, the period. We need to talk about that. What is the period for cosine? What's the smallest value in radians for which the graph repeats itself? What's the wavelength? It's also 2 pi. Yeah. And it makes perfect sense because just like sine, the values start repeating themselves on the next cycle of the unit circle. Okay? All right, so Sahala and Chala. Guess what we get to do now? We get to start sketching transformations of Sahala and Chala. And so let's review that from yesterday. Whether it's a sine or a cosine, this could be cosine now, here's what we have. The absolute value of A is your amplitude, which is your distance the wave travels above and below the center line, which we call the sinusoidal axis, which is your D value. So Y equals D is your new sinusoidal axis, and then from there you would go up and down A units to get your high and low. Your B, the absolute value of it, is the number of cycles in 2 pi. Okay, it's kind of like the frequency. It is the frequency, actually. But it tells you directly the number of cycles in 2 pi. So once you have your B value, how can you find the period? Because B, remember, is like Alex Meissner's accordion. It compresses and stretches the graph horizontally, which will affect the period. So if B is the number of cycles in 2 pi radians, and the default period is 2 pi radians, how can you figure out what your new period is if B is something other than 1? All the periods are going to be symmetrically the same distance, right? So if you have a space that is 2 pi units wide, and you're trying to partition it into B equal units, what would be the width of each one? 2 pi. Let's say I have a unit, a distance that's 10 feet long, and I want to divide it equally into 5 units. What would be the length of each unit? 2. How'd you get that? You took the total distance 10 and divided it by 5, right? Same thing here. We take the total distance, 2 pi, and we divide it by the number of cycles we want to see in 2 pi, which is the absolute value of B. That is the holy grail conversion between P and B. You get B from the equation, the number of cycles you expect to see in 2 pi, the frequency, but to graph it, we're going to need the period. So we convert it by doing 2 pi divided by the absolute value of B. You get the period from the graph, you get B from the equation. They're not the same, but they're closely related by way of that equation. C is going to be the phase shift, which is your horizontal shift, and that's all we need to know for now, okay? So that's what we're going to set out to do next. We're going to sketch, we're going to go to example 5, and we're going to sketch transformations of Sahala and Chala. And I'm going to show you a very methodical, straightforward way to do so. All right, so you walk up to the problem, you see it's f of x equals 2 cosine of 3x. Step 1, when you're sketching a function by transformation, is always to identify the parent function. Pretty easy to spot. Is it Sahala? No. Is it log, natural log? No, not unless you're an egregious misspeller, because ln is not the same as cos. So the parent function is Chala, right? The parent function is cosine. Sweet. So let's go ahead then off to the side, and we're going to go ahead and gather our information. We have the absolute value of A, the absolute value of B, C, D, and then we throw P down there. So I will have you list these things because they're not just values that affect the graph, they actually are meaningful things in terms of the sine and cosine function. The absolute value of A is what we call the what-litude? Amplitude. And what is the new amplitude? 2. Yeah. So that means we're going to oscillate 2 units above and below the sinusoidal axis. What's our value of B here? It is 3. How do we know it is 3? Because 3 is being what by the x? Multiplied. So anytime it's a multiplier, it's either an A or a B. If it's out in front, it's an A. If it's in front of the X, it's a B. Okay? So that means how many cycles are we going to see in a span of 2 pi radians? 3. We're going to see 3 cycles in 2 pi. I will ask you what the meaning of B is, and you'll have to say, since B is 3, we're going to see 3 full cycles in a distance of 2 pi instead of the previous 1. Okay? And so what does that do to the graph? In order to fit 3 things in where you previously had 1, you have to squish them all in, right? So that is going to be a horizontal compression by a factor of 3. It makes total sense now. We got to fit 3 of them in there. So everyone get closer, scoot in, right? Like when you're at a show and you get there early and you spread out, and then people come in the very last minute and the ushers say, "We need everyone to scoot in towards the middle to make room for the latecomers." And you're like, "Crap, I got here early." And now you're like touching people you don't even know. All for the latecomers. All right. What's our value of C? Are we shifting this one left to right or left? Is there a phase shift? No. There's no C value, so it's 0. Is there a D value? Did we scoot it up or down or up or down? No. And so why is D equals 0 important? If you set it equal to y equals 0 is your sinusoidal axis. Sinusoidal axis. All right, so now let's find the period. We know now that we're going to have to squish 3 things in a space where we previously saw 1. The old period was 2 pi, but now if I have to fit 3 things in that same space, what is now the length of each new brand new cycle? 2 pi thirds. Yeah. Good. In general, it's 2 pi divided by the absolute value of B. So we're going to see one from 0 to 2 pi thirds, another one from 2 pi thirds to 4 pi thirds, and then the third one from 4 pi thirds to 6 pi thirds, which is also known as 2 pi. Sweet. Okay, so whenever there is no phase shift, the problems are easier. The problems are easy when there's no phase shift, okay? Because what I'm going to expect you to show on your final graph is nothing but the relevant information. That is the high point, the low point, the sinusoidal axis, and the critical values for the Sahala-Chala. And if there's no phase shift, then the critical values are going to be the same that they were previously. So here's how you are going to sketch this. You're going to draw a y-axis, and now you want to draw an x-axis that does extend into negative land, but goes a little bit further into positive land. Because I'm always going to make you sketch at least 2 cycles, and I'm always going to make you show at least 1 critical value in negative land, okay? But because there's no phase shift, here's what I want you to do. I don't want you to sketch 3 cycles in a space of 3 pi. Because if the B value were 10, I don't want you to try and squeeze 10 things in a space of 2 pi. I'm interested in you kind of stretching out 1 cycle and labeling it. Let the numbers tell the story. So now you're going to come out arbitrarily to almost the end, maybe a little more than, maybe about 3/4 of the way. And you're going to label that the length of 1 cycle, which is what? 2 pi thirds. Good. That's your new period. So here's the bisection method. If you cut that distance in half, you can now label that as what? What's half of 2 pi thirds? Pi thirds. How do you take half of a fraction? You either half the numerator or you double the denominator. So it's 2 pi 6 or 1 pi thirds. Then you do it one more time. You bisect the distance from 0 to pi thirds, and now you call it what? What's half of pi thirds? Pi 6. Now here, I claim there is no more important x value on this entire graph than pi 6. Why? Pi 6 now becomes the distance in between each and every critical value. Your axis high, axis low, axis high, axis low, axis high are always pi 6 away from each other. So we have one more point to label here. If you bisect this region now, you can now label it. That's a 1 pi 6, that's a 2 pi 6, this would be a 3 pi 6, which simplifies to what? Pi halves. Okay? Now let's go ahead, once you have these, and start labeling a few more points. Let's go back to the left. That one is, of course, 0. And let's go ahead now and keep this distance, which is arbitrary, but on your paper, whatever that distance is now, preserve it as you go to the left. And I'm just going to put as many points as I have room for. I have room for 3 more. And let's label them. We're still counting by what? Pi 6. So go to the left, you have negative pi 6, then negative 2 pi 6, which is negative pi thirds, negative 3 pi 6, which is negative pi halves, etc., etc., etc. Now let's go ahead and put a couple more points on the right since we have room for it. I think I have room for just 2 more. And let's label those. Now how are we going to label them? Well, 1 pi 6, 2 pi 6, 3 pi 6, 4 pi 6. This one is 5 pi 6. And the next one is 6 pi 6 for pi. Good. So now you have your x-axis all set up, ready to accept all your critical values, and it's only the relevant information. All right, so now where's your sinusoidal axis? Let's get the y-axis stuff taken care of. It's at 0, so that's nice. You don't have to make a new sinusoidal axis. So now you go to your amplitude, and you're going to go up 2 units from your sinusoidal axis, which takes us up to 2. So again, arbitrarily go up some distance, and now whatever that distance is, try to preserve it, and you're going to go down to negative 2. You have now set the table. You have your x and y axis set up to accommodate really either a sine or a cosine graph. And so now you return to what it was, and you're like, oh, it was who? Chala. And since there was no phase shift, which again are the easier ones, you can go ahead and pick your graphing flavor. I'll choose green, and you can put your dots. So the Sahala and Chala method always reference your starting position, which is the y-axis. Okay, so it would be what? High, yeah, we started 2. So we have a high, and I'm going to go to the, whoa, dang, happy medium here. There we go. High, axis, low, axis, high, axis, low. The axis always has it feels awkward because when you say high axis, the axis kind of like says hi, waves back, and you're like, no, I wasn't saying hi to you. I was just saying high axis, low axis, high. And the axis is like, hi, high axis, hi. No, I wasn't saying hello. Now we go back to the left. High axis, low axis, high axis. And you just put your points all over the place. But we start at the y-axis, okay? So here we go. High, axis, low, axis, high. There's one cycle. Just continue the dots left and right for how many points you have. And now the fun part. We get to eat. It means we get to connect the dots. So here we go. Do them in quarter cycle curves. And don't make them pointy. They shouldn't look like V's. They should be curvy. Now I do want you to do one last thing. On the ends, however far you get, turn the corner and put an arrow, or extend it past and put an arrow, just to signify that the graph actually does what? Keeps on keeping on. Yeah, very good. Now, I always want you to show at least 2 cycles, always at least 2 cycles, and at least 1 point in negative land. Well, we have 3 points in negative land, so we got that covered. Do we have more than 2 cycles? If we start at negative pi halves, that's an axis point going down. So 1 cycle from there would be up to pi 6. That's the next corresponding coterminal angle where we're on the axis going down. So there's 1 cycle. All the way over here to 5 pi 6 would be the second cycle. So we actually have 2 1/4 cycles shown up here, don't we? Yeah, there it is. All right. So what's the domain of this function? All real numbers. What's the new range? -2 to 2. Does this graph still have any symmetry? Still has y-axis symmetry. So notice once you have the graph, I can then ask you any question about it. What's an interval where it's increasing? Well, you could say from pi thirds to 2 pi thirds. Where is a local maximum? That would be the x value. You could say at 0 or at 2 pi thirds. What is the local minimum value? The local minimum value is -2. Okay? Where is an inflection value? We have an inflection value where? Always at our axis points. Pi 6, pi halves, 5 pi 6. Yes, ma'am? The limit will always be d/e. Yeah, by oscillation. All right, so now that we have sine and cosine and we have one transformation under our belt, we will we'll boogie tomorrow. We'll start graphing lickety-split fast. Yes, sir? No, you just put d/e. That's fine. As long as you know why, then I don't have to ask why. But I might ask you why. Things can D and E for several different reasons. All right, 6, 7. We probably will not finish tomorrow, but we'll make great strides. All right, have a great rest of the day.